Hello everyone. Today, our next speaker is Rohit Singh Rathaur. He's a distinguished integrated Master of Science student at Birla Institute of Technology. Rohit is currently a lead machine learning engineer at a subsidiary of ePioneers, focusing on developing climate models for CO2 production and land degradation. Rohit's experience includes roles as a data scientist at ePioneers and product development intern at Pumas AI. He's also interned at the University of Bristol and MIT CSAIL, working on machine learning for partial differential equations and ordering differential equations and algorithm fairness, respectively. Currently, he's an academic researcher at the UiT, the Arctic University of Norway, working on accelerating physics-based optimization problems with deep learning. Please welcome Rohit Singh Rathaur. Rohit, off to you.
Yeah, hi everyone. First of all, good morning or good afternoon or good evening to everyone. And let me share my screen first, so then we will move forward. Okay, so first of all, thanks to Dux for introducing me to this broad audience and for having me to talk about on this particular topic, like which is harnessing the power of machine learning using predictive analytics for sustainable energy from agricultural waste. So yeah, let's move to the next slide. So in this particular session, I am going to talk about we will have some introduction and background about the problem, and then we will talk about predictive analytics, and then how we can use machine learning in supply chain, and then what will be the benefits of this particular thing in the environmental, and what will be the economic benefits, and then we will do a small case study around this problem, and then finally we will have our Q&A session. So before moving to this to this section, so today I will embark on a journey to explore the transformative power of machine learning in the realm of sustainable energy. So sustainable energy is not just a buzzword, but it is a necessity, as because as right now we are facing the challenges of climate change and depleting of fossil fuels. So this quest for alternative and sustainable energy sources becomes paramount. So this is where agricultural waste comes into play every year. And every year, vast amounts of agricultural residues are left unused, often burned, and this leads to pollution. So what if we could harness this waste and convert it into a valuable energy resource? Then this will not only provide us a sustainable energy solution, but also it will address environmental concerns and will offer an additional revenue stream for our farmers. So now, while the concept of converting agricultural waste to energy is not new, but optimizing this process is where always challenge lies. And this is where the magic of machine learning comes in. And using machine learning, or specifically if I will say with its predictive analytics capabilities, so it can revolutionize how we forecast and how we collect and how we convert this waste into energy. So it will not only help us finally design efficient supply chains and predicting biomass availability and much more. So today, finally, we will dive deeper into how machine learning is the game changer in making energy from agricultural waste. Not it is not just a possibility, but an optimized and cost-effective reality. So let's move to the yeah. Yeah, if I talk about a background of this particular problem, then recently the Cell AI had organized a hackathon, and that particular hackathon was very interesting for our team also at Selva Wild and at ePioneers, according to our business needs, because we are also focused around climate finance. So that's why we thought now we should do a business case study around this particular problem. And so this particular case study I will present in the further slide. Okay, so in this particular hackathon, the focus was on the potential of biofuels to lower emissions in sectors that are challenging to decarbonize, such as aviation and marine. But the real challenge was lying in the logistics. So to produce a significant amount of biofuel, a biorefinery required a substantial amount of biomass. So this biomass was scattered across vast agricultural lands, which making its collection a logistical puzzle. Now imagine if you will see this particular spatial residual heat map here. The dark side represents where we are having much biomass. So these are particular in this particular heat map we are having some kind of grids. So these grids were useful at the time of prediction of our future biomass and all. So now imagine having to collect 375 tons of biomass from various remote sensing locations just to produce 75 tons of biofuel. So the transportation of this biomass, ensuring and its quality, and then the intricacies of converting it into a usable form of energy. So it present a myriad of challenges, and this is just the tip of the iceberg. The conversion process itself is multifaceted. It is not just about turning waste into energy, but it is also about doing it efficiently, sustainably, and at a scale that makes a big difference. So today, finally, we will explore how machine learning will help us to navigate these challenges and streamline the process, and to in helping and to make in making via energy not just a theoretical concept, what a practical solution. So now let's move to the next slide. So in this particular slide, I am having three objectives. The first objective is around what is predictive analytics, and the second one real world application which is a biomass distribution in Gujarat, which I have seen the map of this particular state in India. And then the third one is benefits of accurate forecasting, benefits of accurate forecasting. So now let's talk about what is predictive analytics. So as we dive deeper into the world of sustainable energy, so here one tool emerges as particularly potent, so which is predictive analytics. What exactly it is? So as its core, analytics utilizes statistical algorithms and machine learning techniques to identify the likelihood of future outcomes based on historical data. So finally, it is all about making informed prediction, and in the context of bioenergy, it is about forecasting where and when biomass will be available. So now let's take a tangible example to understand its impact. So in the state of Gujarat, India, the challenge was to forecast the spatial distribution of biomass. With a very vast agricultural lands and varying crop cycles, predicting the availability of biomass was no small feat. But with predictive analytics, it became possible to map out region with high biomass yield, allowing for strategic planning in collection and transportation. And the benefit of such accurate forecasting are manifold. Firstly, there is a direct cost saving when we know where the biomass is. Then we can optimize routes, and we can reduce transportation costs, and we can ensure that facilities are located at strategic points. Secondly, it leads to efficient resource allocation. instead of deploying resource blindly, we can focus on high yield areas and while ensuring maximum collection with minimal effort. And lastly, and perhaps most importantly, it contributes to a reduced carbon footprint. So here, like efficient routes mean fewer emissions, and strategic facility placements reduces the need for long haul transportation. So finally, in essence, like predictive analytics doesn't just make the process smoother, but it also makes it smarter and more sustainable and more in line with the goals of a lower carbon future. So now let's move to the next slide. Now here I will talk about like particularly how we are going to use machine learning in supply chain optimization things. So if I talk about mission, so in mission, like so in this particular segment, so I will discuss the role of machine learning in optimizing the bioenergy supply chain. So the journey of biomass from harvesting sites to biorefineries is very, very intricate because it involves collection and transportation and then storage and then finally conversion from like biomass to biofuel. Okay, so each step has its challenges, and that is where machine learning steps in. So why analyzing vast data sets, machine learning can suggest us optimal locations for depots and biorefineries and minimizing transportation costs and time. So if we take for instance the data set provided during this particular hackathon. So by leveraging this data, I tried to design and just to showcase here. Right now, like my solution is not that much optimal, but still I tried my best. So here, like I tried to show and to design an efficient supply chain, and I tried to ensure that biomass travels the shortest possible distance, and it reduced costs and also emissions. So in this whole particular thing, like our vision was to figure out like how they are achieving the energy independence through sustainable means. So why harnessing the untapped potential of agricultural waste, we aimed to reduce our reliance on renewable energy sources. So this didn't only ensures a greener future, but also empowers our local communities by turning waste into wealth. At the now, if I talk about our vision, so at the heart of our vision, like it is the empowerment of local farming communities. So by transforming agricultural waste into a valuable energy resource, we like were trying to create new revenue streams for farmers. So this approach ensure that the benefits of sustainable energy production are felt at the grassroots level. So now here, like if I talk about a model for global replication, so here, like our vision extends beyond the boundaries of Gujarat. So we were trying to build a model that once successful can be replicated globally. So by showcasing the power of predictive analytics and machine learning in sustainable energy production, we aimed to inspire and guide other regions in adopting similar practices. So now beyond the technicalities, so here like I will discuss the broader benefits optimizing bioenergy production. So optimizing bioenergy production like has a direct positive environmental impact. So efficient processes means like a fewer emissions and a significant reduction in our carbon footprint. But the benefit like are not just environmental, like they are economic too. So why monetizing agricultural waste? Farmers can discover a new revenue stream and then turning waste into wealth. And for the energy sector, this may mean a move towards more sustainable and cost-effective energy solution, paving the way for a greener future. So if I talk about first reduced carbon emission, so by optimizing the supply chain and transportation logistics, fewer trips are required. So which may lead to a significant reduction in carbon emission. Now, if I talk about a waste reduction, so in waste reduction, we can efficiently convert agricultural waste into energy, which will prevent the harmful practice of burning it, and it can lead to air pollution and other environmental hazards also. Now, if I talk about conservation of natural resources, so using agricultural waste as an energy resource, so it may reduce the dependency on fossil fuels, which will help us to conserve non-renewable natural resources. And if I talk about economic benefits, so in economic benefits, if I talk about cost savings, so optimized transportation and facility utilization may lead to reduced operational costs. And if I talk about new revenue streams for farmers, so then here agricultural waste, as we know, in the past or currently, like uh, discarded or we always discard agricultural waste, or we want it. So, but now it can be sold as a valuable resource for energy production. And now, if I talk about stimulated local economies, so here the establishment and operation of depots and biorefineries can create jobs and also can stimulate local economies. So now in here I have mentioned how it can help in reducing carbon footprint, and how it can generate new revenues for farmers, and how it can create positive impacts on the energy sector. And now, if I talk about what will be what will be the concept of this problem in business? So, in the realm of modern business, sustainability is not just a buzzword; it is a necessity. Adopting circular economy principles, where waste is viewed not as a byproduct but as a resource, businesses can create value from what was previously discarded. This will not only lead us to environmental benefits, but will also ensure long-term business viability by tapping into new revenue streams and reducing dependency on depleting resources. So now, if I talk about and efficiency in the supply chain is a cornerstone for any successful business. While leveraging predictive analytics, businesses can adopt just-in-time approach to logistics, and while ensuring resources are available precisely when needed. So this will not only reduce cost, but will also mitigate risks associated with overstocking or understocking, and while ensuring smooth operations and satisfied stakeholders. And also modern businesses not thrive not only in isolation but also in collaboration. So engaging with the stakeholders, especially farmers, in the context of agricultural based is very, very crucial. So by forming partnership and providing fair compensation and involving the community in decision making, businesses can ensure a steady supply of resources and foster goodwill. So here, transparent communication further will cement trust and will pave the way for collaboration growth. So finally, in a rapidly evolving world, businesses that innovate will always stay ahead. And investing in research and development, especially in the field of bioenergy, can lead to breakthroughs that will offer a competitive edge. And furthermore, it will also diversify into new markets or adapting products based on changing dynamics, which will ensure resilience and also continued growth. So, it was just a background of the whole problem and how can we how we can it can benefit in the business and all. Now before moving to our case study, I would like to provide the background of this particular problem once again. So as we know, as humanity, why aren't we always have a question in our mind, why don't we use anything at scale, if we are doing any other stuff. So because we know to use anything at scale, it can be expensive, and also it may need some ambitious government targets and substantial subsidies to be able to compete with gasoline, diesel, and conventional natural gas. And even with targets and price subsidies, biofuels present another challenge. So today, 100 tons of crude oil can provide approximately 75 tons of gasoline and diesel. But to get the same 75 tons of biofuel, a biorefinery needs at least 375 tons of biomass. And unlike crude oil extracted from a well, these 375 tons will not be available at a single source location. So instead, they will be thinly distributed across hundreds of agricultural lands, which will be spread amongst multiple geographies. So as right now you can see in this particular residual map. So here, let's say in this particular map, to set up a biorefinery in a region, an understanding of the region's current and future biomass produced will be required. So this biomass needs to be collected and transported to intermediate depots. Because we will have to demoisturization and densification into pellets. Then the pellets will then be transported. Yeah, here if you will see, this is let's say it is our harvesting site, and then we will have to figure out where we will pre-process this harvesting material, and then finally transport it at the biorefinery location. So to figure out these two locations, pre-processing depot and biorefinery, so here we will need of supply chain concept. Okay, so the overall problem statement was around converting waste into energy. So if you will see this map again, let me repeat once more. So this map corresponds to the yearly residual biomass, which is available in the state of Gujarat, which comes in the western part of India. So the geographic region is divided into equisized grid blocks, and the average biomass production of each block is represented on the color scale, which you will see here. And then the spatial distribution will change year after year, and the biomass available in these grid blocks will serve as a feedstock to biofuel production plants, biofuel production plants, that is biorefineries, which I mentioned here. So here, the biomass feedstock needs to be optimally collected and transported to the biorefineries gate and the grid blocks. And then the harvesting side will serve as the starting point in the supply chain. So at each harvesting side, biomass availability can be forecasting using historical data, and then external parameters such as weather, rainfall, or government regulations may also influence the biomass production. So bales of biomass will be collected from these harvesting sites, and then it will be transported to the pre-processing depots for densification and pelletization. And then the pellets, from here, the pellets will be transported from each of these depots to each biorefinery in quantities that cater to each biorefinery's demand. So the location of depot and the biorefinery will remain constant if you in this particular thing. So here, I tried to accurately forecast the spatial distribution of biomass from these harvesting site. And then I tried to select and I tried to find out some optimal location for all the assets in the supply chain, that is pre-processing depots and biorefineries. Okay, so now we were having some data around it. So if you will see this table number 1.1, so this table represents it is a time series of biomass availability in the state of Gujarat from year 2010 to 2017. So in that particular residual heat map, they had given a arable land as a map of 2,418 equisized grid blocks known as harvesting sites. So for ease of use, what they had done, so they had flattened the map and provided location index, and also provided latitude and longitude, and then year-wise biomass from 2010 to 2017. And if you will see in the table 1.2, this table is all about distance metrics. So in this table, it is the travel distance from source grid block to destination grid block. And then they provided this data as 2418 by 2418 matrix. So it was a very huge matrix, very high dimensional matrix, and that's why it was to find the optimal location, computationally, it may be very expensive. So accordingly, we will have to decide about our methods and all. And yeah, so now if I move to the next slide. So here, I did some exploratory, as we know, before moving any ML problem, whenever we have some kind of data set, we should always try to do some kind of data analysis. So we will have an idea about the data, what this particular data is representing and all. So here, in this particular thing, I try to first I try to check for missing values, and then I computed the summary of statistics. I computed summary statistics to understand the distribution of biomass availability. And then further, like I visualized the annual trend of biomass availability, and then I tried to visualize the spatial distribution of biomass for a particular year. And then I also checked the correlation between biomass and geographical location, which we will see in like further slides. So before moving to the next slide, first I will talk about this particular table. So this particular data, this biomass history data, was not containing any missing values. So this was a very good thing, as we don't have to handle missing data introduction. So now this summary statistic tell us about the distribution of biomass availability for each year from 2010 to 2017. So if I talk about this particular column, the mean column, so the mean biomass availability seems to vary slightly from year to year, but generally it is around 130 to 160 units. Now, if I talk about the standard deviation, then the standard deviation is quite high, and it is it indicates indicating a large variation in biomass availability across different harvesting sites. And the minimum value is almost zero every year. So it is indicating that some sites might not be producing any significant amount of biomass, and the maximum value is quite high compared to the mean, indicating, and it is indicating the presence of sites with very high biomass production. So now further, I will visualize the annual trend of biomass and the spatial distribution of biomass availability for a particular year. So if I talk about this particular graph, so this line plot shows the average biomass availability from 2010 to 2017. So here, we can observe that the biomass availability generally fluctuates year, over the years. If you will see from over the year. Okay. So the highest average biomass availability was seen in 2013, and there was a slight decrease in 2014 and 2015 also, and followed by an increase then in 2017. So now, in the next plot, I will visualize the spatial distribution of biomass availability for a particular year. Let's say for the year of 2017, to understand the variation of biomass availability across different locations. So here, I used a scatter plot where the size of each point corresponds to the amount of biomass available at the location. So, so this particular scatter plot displays the spatial distribution of biomass availability in 2017. So each point represents a harvesting site here, and the size of the point corresponds to the amount of biomass available at the location. So if you will see, the bigger size means we are having a higher biomass. And for this plot, we can see that biomass availability varies across different locations in this particular region. So some region have higher biomass availability represented by larger points, while other regions have lower availability represented by smaller points. So this information is very important when deciding where to locate depots and biorefineries, as regions with with high biomass availability might be more suitable for settling up these facilities. Now the next step, would we check if there is any correlation between availability and geographical location? But we will have to keep in mind that the relationship between location and biomass availability could also be influenced by various other factors like soil type, rainfall, and temperature, etc., which I had already mentioned. And these factors are not included in the current data set which they had provided. So for further analysis, I figured out we can do a few, we can plot several other visualization which can be useful for our analysis. So here, I tried to do histograms of biomass availability because it can help us understand the distribution of biomass availability for each year or across all years. So this will provide insights into whether the biomass availability is skewed towards certain values and whether there are any outliers. And then I also presented box plots for yearly biomass availability. So box plots was giving me a summary of minimum first quartile, median and third quartile, and maximum biomass availability for each year. So it showed me if there are any outliers in the data. And then I also represented the heat map, and then I also represented the time series plots for selected locations, and then further I represented the spatial heat maps. So I will describe all these visualization one by one. So firstly, I will talk about these histograms of biomass availability. So that's here the histogram is showing the distribution of biomass availability for each year from 2010 to 2017. So we can see that the distribution is positively skewed, and with many locations having a low biomass availability and few locations having very high biomass availability. And now in the next slide, I will talk about box plots for yearly biomass availability. So here these plots these plots are giving a summary of the biomass availability for each year. The median biomass availability seems to be very relatively stable over the years. However, there are several outliers, especially on the higher end, indicating some isolations have significantly higher biomass availability. And in the next plot, here I have represented this correlation matrix and time series plots for selected locations. So heat map for correlation between years, this particular heat map shows that the biomass availability between different years is highly correlated, as you can see here. So this suggests that locations with high biomass availability in one year tend to have a high availability in other years as well. And now if you will see in the time series plot for selected locations. So this plot shows the trend of biomass availability over time for a few randomly selected locations. So here the biomass availability seems to fluctuate over the years at these locations. So these visualization helped me into the data and also guided me in the next step of forecasting and supply chain optimization. And then I did some data analysis around distance metrics also. So I followed the same steps as I did for the biomass history, and then I tried to plot the distribution of these particular distances. And then after all these data analysis, now it was time to jump on this second part of the problem. So before moving to the like before moving to second part of the problem, here I will try to explain the pipeline of the problem. So it is all about like data preparation, and then it is all about biomass forecasting, and then after forecasting, like for the supply chain optimization, we were having some kind of constraints like this we needed to handle. The constraints were like to ensure like non-negative values and limit biomass procured, and then limit depot capacity and depot and refinery count, and the process of biomass should be at least 80%, and we also need to balance between depot input or output, and then finally output preparation, and then evaluation and iteration. Then again iterate it if like we are not getting any satisfactory results. So now I will show you some implementation part also before moving to our Q&A section. Sorry, from where I will cancel it. Yeah. So here, like I just implemented a few kind of techniques. So first technique was like few time series techniques. So first technique was halt Winter's exponential smoothing technique, and then after seeing the forecasted results for the year of 2018 and 19, then I tried different algorithm to make the comparison between the results. So the different technique was linear regression model. Then again, like here, I forecasted the biomass for the year of 2018 and for the year of 2019. And then I calculated some metrics of around which algorithm. The metrics was mean absolute error and mean squared error, and then overall root mean squared errors. And then finally, I also experimented it with the ARIMA model, which is a very common algorithm for the time series problems. And then I compared all these three results together, and then I did some error analysis around all these three methods. So then I had some conclusions around these error analysis, and on the basis of these error analysis, I again forecasted it using ARIMA. And then still like I was not getting some kind of satisfactory results. Then I thought now I should try some kind of neural networks. So here I tried firstly I tried a feed-forward neural network, which is basically a multi-layer perceptron neural network. And then I also tried some kind of other neural networks. Then those were RNN or LSTM and GRE. So these are very well-known algorithms for the time series problems. And then finally, I thought I should try some kind of Bayesian approach for this problem. So I just experimented it with Bayesian auto regressive time series. But for this problem, the collab, I am showing just for experiment, like just for demonstration purpose. But all these experiments, I had run on my own server, where I was having very very big system and all to run this particular problem. And after it, after getting the results from all these methods, I just my next and final step was to optimize, was to find the optimal location of biorefineries and the second factor. So finally, I just used the forecasted biomass data from which I had got from different methods, and then I tried to find the optimal locations. So the first approach I used, like I thought, like even like I think like we should always before moving to the advanced solution, we should always use some kind of brute force method or some kind of heuristic optimization approach. So the same thing I did in this like in this particular problem also. So I just use some kind of heuristic optimization approach and then brute force approach. Then finally, like I tried linear programming solvers, which was ILP and other solvers. So that is all about this particular problem and all. So I will provide this the link of this problem and link for the data set also, and the implementation link also, so you can also experiment with this particular problem. Now, like in conclusion, before wrapping it, this particular session, so I would like to emphasize like the transformative potential of machine learning in the realm of sustainable energy. So the journey from agricultural waste to energy like is not just a technical challenge, but it is also an opportunity to reshape our energy landscape, which can empower local communities and which can also pave the way for a greener future. So here I am optimistic like about the strides like we can make together in this particular domain. So finally, like thank you for your time and attention. So do you have any further questions or wish to like dive deeper into any aspect we discussed today? Please don't hesitate to reach out, and further we can also collaborate and drive this vision forward. So if you are having any question, then please let me know.
Well, I don't think we have time today for any questions, Rohit, as we reach the end of our session, but thank you so much. It was great listening from you and talking about biomass. But yeah, please reach out to Rohit